All right, so I'm here to talk about interaction interfaces. I happen to work for Leap Motion, but I want to talk about a whole variety of things and some motivations for how to design around them, but more importantly, how to design for them. Thinking about physical things we're going to make. I know there's a lot of things to make this weekend. I focus a little more closely on robotics, something we can move around and manipulate. So let me get started. So I hear that you're building a robot, is that right? Is it going to look like this? Probably not. Maybe a little more humble, like a MechWarrior from MechWarrior 2000. I remember playing 1994. What a sweet game. It's probably not going to look quite like that, but a little more like Wall-E or Johnny 5, right? Simpler, smaller, more manipulable, even have some treads on it. But since we only have maybe 24 hours here, it's probably going to look a little more like this. Has the classic Johnny 5 treads on it, but there's also like a breadboard and Arduino sticking out the top. Instead of treads, you might also have wheels. Something like this. So this is kind of one of the models you could deal with your, something to roll around on the ground with your robot. You could be a little more ambitious and try to build a hexapod, like a spider-like or an insect-like thing. But again, it's not going to look quite that sexy. It'll probably look a little more like this, which is still pretty damn good, I would say. You have 6 legs there, and it's carrying around its laptop, so it has a brain with it. It's a centralized nervous system on this spider, which is better than the octopus has, right? You might even go even farther from the legs and try to attach arms to it and build a Terminator robot. But again, it won't look like this weekend. It'll look a lot more like this. Or you may even try to put multiple things together, treads and arms, and have some horrible, disgustingly scary thing like this, which there will probably be small children in the room who are going to have a nightmare about this machine attacking them. I'll talk a little bit about these, and very, very briefly just mention that also drones are another option, but since you just heard about drones, I won't focus too much on them. And I hear autonomous drones are all the rage. I believe we have some parrots on site, or if you built your own, it might look more like this with, again, the breadboards and wires bursting out the top. I'd also like to mention a robot that I've had to dealt with in the past week. Just a few weeks ago, we made a relaunch of our store, redesign, and so to celebrate, one of our web engineers got this little balloon helium-filled fish here. It's like a little blimp, and on the back it has a motorized fin, and it has very simple controls. We blew this up and naturally flew around the office and had fun celebrating. These are just all the possible array of robots you might have. The question is, how do you control them, right? There's all these different wheels. There may be flying. It may have arms, things like this. So now we get into the interaction of it. If you're going to control this in real time, most likely you're not going to be sitting there on a terminal and controlling it with text, although that is an option. You're going to want to have some sort of something more interesting, more natural. And as we heard from Worley earlier, we're all lazy, right? Or at least the smartest engineers are the laziest, he claims. So the simplest possible solution is for every servo on the robot, maybe we'll have a button. So if you just have a motor and you have one axle on the rear wheel, your rear axle is servo controlled, you maybe just have one button on your robot. Go, and then you let go, and that's don't go, right? That could be as simple as possible. Maybe you don't even use the joystick on our favorite Atari 2600 controller. But again, this button is discrete. Maybe it's continuous on an RC car where typically there's only 2 things to control, faster, slower, and then also left, right. This is a very classic looking remote controlled car controller that we've seen. We have the trigger to control continuously how fast or slow we're going, and oftentimes if you push it forward, you can actually apply some brakes to the RC car. And then we have a wheel on the side. You're turning left and right, and again, that's in a continuous fashion. In the center, there's a neutral zone, and then you're going to turn a little more to the left and to the right. So these are all very, very good options that have been explored. Probably all seen controllers like this. But what if your robot has more functions than that? What do you do? Do you add more buttons to your controller and come up with something like this? This is actually a musical instrument, by the way. It's called a monome. There's 512 keys here, and you can do beat sequencing. And behind every button is an LED, and you can see the feedback of what you're controlling on the computer. It's a beautiful musical instrument. However, I don't think this would be very effective or useful at controlling a robot. You'd probably want something that fits your hands better. Maybe you don't need 512 buttons, but something fewer. And you're going to need some continuous controls. So again, from music, this is Muldo, a DJ who makes his own instruments. Following turntablism, he has pushed forward an art called controllerism, where he makes his own musical controllers, custom fit to his hand, and he can do amazing, beautiful things with this. This could be an appropriate control if your robot has many functions. You've got buttons for these discrete or binary possible effects, as well as sliders and knobs for some sort of continuous controls. But this isn't going to be very intuitive to control something like if it has wheels or you're flying around. You're going to want something more like this, which is what a professional would use to control a flying plane. And in fact, there's one in the room over there on our Heroku friends have one to control their tiny little, I think it's called a Crazy Fly drone. There it is. In their case, they only use 4 of the controls to control pitch, yaw, roll, and height. And there's many other switches that a fancier drone or airplane might use. But this at least affords you some more intuitive control, especially it only takes a little while to get used to this, and many of us have played with RC cars as kids. You'll be able to pick this up and control that drone or that plane very easily. You could even use this to control something rolling on the ground. Like you could use this for an RC car or a robot with treads. You could probably use the left and right to control it like tank treads, much like Katamari Damacy, which is for the PlayStation, and that's why we use the DualShock controller there on the right. These, again, are more ergonomic and meant to sit in your hand for 8 or 10 hours or however long Microsoft wants you to be playing there. And these not only are more comfortable, but they're portable. These are wireless. You can control it. You could walk around outside with it and follow your robot. And then it helps avoid the Resident Evil effect, which is if you have something with kind of tank controls or RC car, if your orientation is the opposite of it, it becomes very difficult to visualize left and right. They're mixed up. Whereas if it's facing the same direction, it's easier to visualize. And if it's a more complex, instead of just adding more buttons to a massive controller like this, you have a specialized setup. It's known as Steel Battalion is the game. And this was sold, I believe, for Dreamcast and Xbox, just to really get the full experience of playing this game. It's somewhat like a Mech Warrior, where you're controlling a very large tank-like thing. It's overwhelming to me to see all of these controls laid out, even though they're kind of put in a specialized way that may become more natural. It looks like this. There's just so much information in your face. What do you do with it? So there's kind of a balance, like how many things are there to control on your robot, as well as how much information do you need to get back from the robot. And they're completely different styles, rather than just buttons and levers and joysticks and that sort of thing. You could actually use your body in free form, a very different type of control. And if this game, Steel Battalion, they later ported to Xbox, sadly, it was a disaster. From what I've heard, the experience of playing Steel Battalion with the Kinect, worse than what you might imagine playing Assassin's Creed is. There was a great video people put online, a spoof that they made Assassin's Creed for the Kinect. And down here, this is an Intel Creative camera. They're both depth sensing cameras. So it gives you, the information it provides to you is how far away are things in the world. It's much like a video camera is a color map of a square view of the world. This will provide you a depth map. Looks something like this. Here, this happens to be libfreenect, the open source hacked version of the original Kinect libraries. It's heat map colored to show you depth. So the hand is closest to you, then the arm and the person, and this other square thing on the side or the next farthest. And then in the very, very back, it's dark blue and black. But how do you interpret this information and actually make it useful? That is a challenge. And one of the things that libfreenect community has done, it's called the OpenNI project. They built skeletal modeling on top of this, which Microsoft did internally, but that, of course, was not available to people who hacked the Kinect originally. So now there are 2 different libraries that you can use with the Kinect. The sanctioned Microsoft one, as well as the open source, quote-unquote, hacked one. And you'll see what it does is provide you articulation points to different joints on the body. Sometimes it does actually require an initialization step. You'll need to stand in front of the camera in a very clear T shape like this, and then it's like, oh, yeah, that's certainly a body. And then it can track from then on, and you can do more interesting things. But if you just kind of are hunched over, you enter the field of view, it may not be able to recognize that you're a human. Once you've done that initialization step, it now has this basic skeleton model of your joints So, as an example, you have the shoulder, the elbow, and the hand, 3 joints provided for the arm. And then you can do interesting things like this. With this, for example, there are physical therapy programs that have been written where maybe a kid is playing a game, and the exercises, they need to exercise their leg in a certain way to build up muscle mass that they've lost due to an injury or something like that. So you could use this to actually create a game for that example. And this is like what is often used when Kinect is used to control games, or like the dancing games. And if you had a robotic arm, much like I showed you in the video earlier this morning, you could use that whole arm to control the arm information coming out of the Kinect skeletal tracking API to control the arm in space. But in this case, you wouldn't have any articulation points on the hand at all because you just have one for the whole hand entirely. So that's where a different type of sensor may be more useful. In this case, a leap motion controller, which also uses infrared light, but it's a very different technique. And instead of providing a depth map, we directly provide hand and finger information. So we'll provide, for example, a basis on the hand, fingertip positions and directions of the finger. And we even track tools. You can do pencils and pens and chopsticks and that sort of thing. And in the upper right is an example of a gesture. Circle gestures and taps and swipes and that sort of thing. And you can build your own more customized gesture recognition on top of that. And this may be useful for a couple of different things. I'll show you a demo in just a moment of a type of interaction that I think is very natural and how we can actually apply this to a robot situation. I would like to mention, unless the joints on the robotic arm perfectly map to joints on your arm, you will have to do some additional work, which is the inverse kinematics problem of which this is what Eugen did in the video I showed earlier of the robotic arm. He used the position of his palm coming out of the Leap Motion API and tried to move the robot's arm in such a way that the tip of it is in that position. But that's very different from the servos, how the servos work. And so you'll need to solve essentially a math optimization problem with physical modeling, and there's constraints about the lengths of things and how far servos can move. And in order to find the angles that you're trying to adjust the servos toward, to actually get the position of the end of that arm in the right place. And if you're, in this case, we have 3 flexible joints and a total of 7 servos here. So you'll need to solve a math problem to do that. A lot of this is available for free online, and you can use it as a starting point, but you'll need to tweak, and there's a little extra work to do. Before we get into exactly how to connect these two, I want to show you a demo of what you can do with the Leap Motion controller that I think is a very compelling interaction style. So here we are on Amelia Island, and my hand, let me raise the leap up a bit more so you can see exactly what I'm doing. If I put my hand in the zone, it should track where my hand is, and in the center of this space, there's essentially a dead zone where nothing interesting happens. You'll see this little point in the center of the screen. That represents the position of my palm. And using just the height, I can go away from the ground, and I can pan left, pan right, and even fly forward a bit like that. So there's 3 different axes I can move along with just the palm point. I can also twist my hand. I can use yaw to rotate around like this. I can also tilt up to look more at the sky, tilt down to look more at the ground. And of course, roll does not work because they do not support rolling the camera in Google Earth. But if I combine these actions together, I can get a fairly natural movement, kind of like a helicopter ride over the city, back up like this. And here we are on Amelia Island. I'm going to zoom out to all of Florida. I'm so glad the Wi-Fi works in this room. Here we have the state of Florida. And I'll quickly fly to Manhattan to show you what a fly-through over a city with buildings looks like. Let's go down Wall Street. We can fly through the buildings, and let me zoom around this new tower that we have. And then get a little wider field of view of the whole city. Hopefully there are some New Yorkers in the room. And this little subtlety I did at the end is I closed my fist and then removed it from the field of view. If I didn't do that, I would have backed up before then. A null gesture in some sense, it means don't interact at all. I'm not interested in interacting with my hand as a fist. This, I think, is a compelling experience because it may take just a minute or two to get used to the sensitivity of it, that it really is very fine-grained control. But in a matter of minutes, you can fly around like a helicopter, and you're not holding a controller with many joysticks on it. You're using your hand as you naturally would if you're playing with a kid doing an airplane game like this. And I think it's a really fluid and natural way to move around a 3D scene like this. And you could very easily connect it to a quadcopter. I think I showed a video this morning of someone who did it in LabVIEW. In a matter of 24 hours, they did something like this style of control with a quadcopter. You could do something similar with an airplane as well, but then you have different constraints because you can't pan left and right with an airplane, right? So now that I've shown you that, I want to talk about how do you actually connect this to manipulating servos, different motors on a robot to actually get what you want. So as I mentioned, we had this fish in the office, which is remote controlled. If you can see it, there are exactly 4 buttons beyond the power switch because there are 4 ways to control this, this fish. The fin on the back, much like a real fish, can go left and right. And then there's a counterbalance. It pitches the head down, or if it slides back on the belly of the fish, it goes higher up because it's offsetting the helium in there. And this is exactly how you control it. If you want the fin to go to the right, you press right. But that doesn't turn the fish to the right, it just moves the tail. So you literally have to move this control left, right, left, right, left, right in order to swim this fish. Much like how the spinal cord of the fish would be controlling its fin, but at the cognitive level, the fish's brain is not really doing that. And that's what I'm would like to argue is this is the way to design a robot control is to think back about the cognitive level and the spinal cord level. When I make a movement like this, walk forward, I'm thinking about I want to move forward. There's a goal in mind. And my cerebellum and spinal cord together are doing the whole orchestra. They're the conditions for the orchestra that is the musculature of sending acetylcholine down my spine to make the muscles actually to work in symphony. And in this case, instead of left, right, think about I want the fish to swim forward. And I had made the unfortunate mistake of changing the code. I made a cardinal sin in demos, live demos. I changed the code just moments ago, and it's slightly broken, but I will fix it and have it available soon after this talk, in about an hour. I'll bring the fish in, and you'll see with the Leap Motion controller in that same control scheme, I can slide my hand forward, and the fish begins swimming forward, and the tail moves. And if I go farther forward, it'll move faster and faster and faster and faster. And if I pull back, the back tail just stops. And I can tilt my hand up and down to pitch the fish. And so I simply tilt up and move forward, and it begins swimming up and forward. As our hardware engineer on the right, since he deals with infrared light all day long, he decided to just simply read what's coming out of the remote control, and he built us a circuit that sends over the serial port with a USB connection infrared light, and we can just beam it straight to the fish. And then Peter on the left, one of our web engineers, built an app, which unfortunately I don't have enough time to show you much of, to actually control the fish in a much more natural way, swimming forward, tilting up. And I think the major difference that worked really well for him is that he had a goal-directed approach. And I'll very basically show you the architecture. I hope you can read enough. The basic architecture is you have an app. It synthesizes 2 parts of data. The fish service, as he called it, is the spinal cord. It talks about, okay, what's the goal? Now let me turn that into move the muscles, move the fin, tilt the pitch up and down. And this converts something like a let's move forward command into moving the tail back and forth at a certain speed, depending on how fast or how far forward your hand is, the fin at a faster and slower pace. And then over here, the leap service that he wrote is the other side of it. Given the hand data coming out of the Leap Motion API about the pitch and the tilt and the position and all of that, translate that into a goal. So if your hand is moving forward, the goal is let's swim forward. And if you come back, let's stop swimming. This is the architecture is split. It's interpreting the input to the goal and then sending that off to the app over here. The app is listening for those goals from the Leap service and then sending that to the fish service, and the fish is then turning those goals into actually moving the fin and tilting up and down. And again, I'll have this robot here hopefully in a matter of an hour or so and show you, and I can explain more about the code. This little CoffeeScript app which I'd also like to make a call out to. It uses the Node WebKit serial port library, thanks to our organizer. If there's any time for questions, maybe I'll take a question. I guess we're going right to the next one. Thank you very much, and I'll see you later with the fish. Woo!